Hello everyone. In this video, I will share our latest work on the area of multi-robot reconstruction. Coxgraph, multi-robot collaborative globally consistent online dense reconstruction system. All authored are with State Key Lab of CAD and CG in Zhejiang University, China. First of all, we need to understand what an important role multi-robot reconstruction systems play in real-world applications. Although existing single robot reconstruction systems have shown their good performance on online localization and mapping, they are still difficult to be applied in large-scale scenarios such as city-level reconstruction and time-critical scanning tasks. In view of this, we highlight that multi-robot collaborative dense reconstruction deserves more attention as they permit rapid exploration and higher redundancy than single robot systems. However, certain challenges exist for multi-robot reconstruction. Firstly, the maintenance of global consistency across all robots of both localization and dense maps. Secondly, the high bandwidth requirement for dense map data distribution limits its application in real world. So far, for the localization challenge, there are many efficient multi-robot visual SLAM systems which already satisfy the real-time and accuracy requirement for reconstruction tasks. For example, the SLAM systems listed below: CVI SLAM, CCM SLAM, Corp SLAM, and Win Client Server. They share a similar style of localization across robots, sending key points, landmarks, and feature vector or back-forward vector to the server to search for loop closure matches and then check its geometry consistency. In this work, instead of developing new localization methods, we focus on combining the existing multi-robot visual SLAM systems with dense construction modules and form an entire complete multi-robot reconstruction system. For dense mapping tasks, there are also a few systems existing, for example, CoScan, and the paper Multi-Robot Coordination with Agent Server Architecture for Autonomous Navigation in Partially Unknown Environments, in which the Win Client Server SLAM mentioned above is proposed, and the most recently Chimera Multi. While most of existing multi-robot reconstruction methods try to perform dense reconstruction, they either assume high-quality network connection among clients and focus more on task distribution and collaborative path planning, or only optimize and transit trajectories. They adjust only local dense maps. Note that none of them can achieve global consistency of dense maps with limited transmission bandwidth. In conclusion, in this work to tackle these problems, we propose an efficient system named Coxgraph for centralized multi-robot collaborative dense reconstruction in real time. We present a compact transmission representation which enables transmitting local 3D submaps with minimal bandwidth requirement. Our system achieves global consistency across robots by extending online map fusion optimization and loop closure correction methods. As shown in the figure, our framework consists of multi-clients and a centralized server. In client side, there are visual odometry front-end module, and dense submap building module, and a mesh pack generation module, also known as submap compression module. In server side, there are client handler modules responsible for receiving and recovering submaps from clients, and loop closure detection module works the same way as multi-robot SLAM system mentioned above, and optimization module which optimize over registration, odometry, and loop closure constraints adapted from the optimization methods of Coxgraph. Now we talk about Submap Transmission module. In this module, to achieve transmission of dense submaps with minimal bandwidth, submaps are converted to an intermediary data format named as mesh packs. including 3 types of information. Firstly, mesh triangles, including its points and colors. Secondly, indices of frames in which each of the triangles are observed. Third, trajectory of each submap. These mesh packs are sent to the server and recovered to TSDF submaps by converting mesh triangles to point cloud and reintegrate to submaps, according to the frame poses they get observed. By this method, we are able to significantly reduce the bandwidth requirement, but there is still an obvious problem, which is, consider each mesh triangle has only 3 points and their colors, so about 18 numbers in total, either integer or float. But the frame indices of observation can be easily multiple times larger than 18 numbers, which takes a big part of bandwidth. So we propose a method to trim the frame indices vector by extracting effective subsequences from them and use the first and last indices of subsequence to represent them. By doing so, we are able to reduce bandwidth requirements to only 10% of the original. The compression method is evaluated in the experiment section. Now, given the ability to transmit dense maps with low bandwidth, we can perform loop closure outlier rejection based on dense information. 2 steps of outlier rejection we employ in this work. The first step is named as trajectory collision check. The basic idea is for every submap pair of loop closure candidates, the trajectory of one submap, if transformed to the other submap, it should still fall in free space in the second submap. If too many points fall in obstacles of the second submap, we consider this loop closure candidate is invalid. The second step is named as fitness check, firstly proposed in features. Given a correct loop closure transformation, isosurface points of one submap, if transformed to the second submap, should still fall in the isosurface of the second submap within acceptable error. If too many points don't fall in the isosurface, we consider this transformation is wrong. Next, we talk about optimization. As mentioned above, we adapt the optimization process in Coxgraph to work in our multi-robot system. Similar to Coxgraph, we also build 3 types of constraints. The first type of constraint is loop closure. The basic idea is given a loop closure transformation between 2 frames from A to B, submap poses should be aligned accordingly. If not correctly aligned, the residual can be formed based on the transformation error. The second type of constraint is odometry constraint. Similar to loop closure constraint, the same alignment requirement also applies to transformation provided by odometry. If not correctly aligned, the transformation error will be the residual. The third type of constraint is registration, or correspondence-free registration, also first proposed in Coxgraph. In conclusion, it's solely based on ESDF dense maps, of which the principle is the isosurface point of the first submap, if transformed to a second submap, should also fall in isosurface ideally. But if not, the distance value in voxels are able to represent the constraint residuals. We build the post graph as shown in the figure. Red lines mean loop closure constraints existing between loop closure matches. Odometry constraints as green lines between adjacent submaps, and registration constraints as blue lines between any overlapping submaps. We optimize submap poses based on these 3 constraints, and after optimization, we generate client coordination transformation for localization and a global dense map and its mesh. We firstly test the performance of the proposed submap compression method. We use Wins, Mono, and Workbox to reconstruct Icon Room and Machine Hall scene into dense maps and compress, then recover them back. Then compare the reconstruction RMSE between the maps. As the table below shows, the compression and recovery process only cause a really small error. Secondly, we reconstruct the first, second, and third sequences of machine hall at 3 clients, using depth maps from stereo matching. We evaluate trajectory, reconstruction error, and bandwidth usage. As seen in the table below, our method provides a high accuracy in reconstruction both in direct mode, which means without compressing submaps, or in compression mode. Below are figures of 3 client trajectories and reconstruction result colored by client ID. Here are graphs showing the bandwidth usage of different types of messages in our system. As we see, without frame indices trimming, mesh packs are roughly 30 to 50% of the size of raw SDF maps. But with trimming, the bandwidth down to only 10%. At last is the platform experiment. We reconstruct our lab using 3 clients. The bandwidth usage is listed in this table. As we can see, the system works within bandwidth 100 kilobytes per second. The visualization of reconstruction result of our lab is shown below in this figure. The result shown above is produced by our system working with Win's client server, and we have another video showing our system working with Corp Slam in RGBD odometry mode. This is our low bandwidth online multi-robot reconstruction system, Coxgraph. Thank you for watching.